Okay.
Good morning.
Everybody is awake?
Yeah.
Okay. All right. So today's talk is kind of important because I have been. This is like kind of like some important work that we did before, and and right now I think what we're trying to work on is kind of like closely related to this, or we needed to consider it because, like the list for the project that I'm leading really, like some of the action items related to this, like we needed to know it and then to better evaluate, what should we do for the action items. Okay. So I changed the title to be Quasi-crystals as solutions to geometric frustration. So see, that's a quasi-crystals. So it's plural for multiple quasi-crystals and each as a solution to the geometric frustration. I will be focusing on only one actually, but it's good to know that this one quasi-crystal is part of the solutions to the geometric frustration. Okay. So solutions for geometric frustration through curvature. There are different ways of releasing the geometric frustration. Oh, okay, sorry. I was thinking of adding a definition for geometric frustration, but I forgot about it. So geometric frustration kind of is only being brought up in Sadaka book, I think. Like that's a whole book on geometric frustration. It talks about, like in a four-dimensional space, we can use the tetrahedron that tau the curved 3D space perfectly. But when we flatten the curved 3D space, when it becomes Euclidean 3D space, the tetrahedron can no longer tau the 3D space. So then there is a frustration there. Like I showed before, like we have a 5 group, and then like there has to be a gap. That is kind of a little frustration there. Or if we put 20 tetrahedron together in this fashion, right? There will be gaps or twists or whatever. So there's also that, we can name that frustration. So
giving examples of frustration.
Yeah.
But is there a mathematical expression that expresses frustration?
Mathematical expression.
Yeah.
Well, that's what I'm trying to say. Yeah, I mean the solution or expression kind of like means similar thing here. Like whether you distort the tetrahedron, right? You make the edges get distorted, you can still tell the space. And that's a way of expressing the frustration. Or you can use through curvature, right? You curve the 3D space. You can also express the frustration in that way. But either this distortion or curvature or twist, all these are kind of like there is some kind of, we can think as a torsion, tension in that. So it is, can think of like kind of force-like thing.
Can you relate, you've once explained it in a way that's very nice, where you said that when you have the higher dimensional space, you have the vectorial freedom for certain patterns. And then when you project it, you crush down to a lower number of dimensions and you create the idea of a tension, the pressure of crushing down to lower dimensions. So
yeah, I will have some mathematical notebook on that. So this is just an outline. Okay. So anyway, so solutions for geometric frustration can be through curvature, and that is the E8 to 4-dimensional quasi-crystal. Well, okay. So maybe I should better say the kind of the 600 cells in the E8 to 4-dimensional quasi-crystal. because it's this E8240 quasi-crystals are kind of made of intersecting curved three-dimensional spaces. So it's the curvature that releases or resolves the geometric frustration or expresses the geometric frustration. So make it a perfectly tiled space. There's no gap, no twist, no anything. Right? So I'm not gonna talk about that. And then there's a solution. Okay, so that shouldn't be an S there. Solution for geometric frustration through distortion. That's a E82 3D quasi-crystal. I will be showing this part. Okay, so I can show you how the tetrahedron get distorted when we project the E82 to 3D, and then so yeah, I'm
But
gonna
why
show.
are you, it doesn't seem that we should separate those because the distortion is in the E8 to 4D quasi-crystal where the Gaussian polytopes get distorted, unless you're focusing on
No, the tetrahedron. There is no really distortion here.
the Gaussian polytope distorts to the 600.
Well, equally. Yeah, the tetrahedron shrink to the same ratio, so it's still a regular
So
tetrahedron.
contraction is not a frustration?
Well,
It's an expression of it.
I mean, if that's the case, then I have to say through distortion. That's a distortion.
No. Irrespective of what you're saying there,
Mhm.
I'm asking a question. It's a contraction.
Yeah.
Which is a scale down.
Yeah. Well, I would say, if this whole object constructed equally, I don't want to call it this frustration because geometric frustrations really deals with whether this object can tile the space, or not, if there's gaps or not. So if everything just shrink all equally, I don't think there is, frustration in this sense.
Because
That's lost. At least that's not the geometric frustration
because the
as
600
defined.
cells cannot tile the space.
No, but that's what I'm saying. It's a curved 3D space. 600 cell is a curved 3D space. That's why the geometric frustration is released through curvature. I shouldn't say, I can remove the E8 here. It's really like the four-dimensional quasi-crystal has all these four curved 3D-dimensional structure. Maybe I should say 600 cell, or curved this three-dimensional space. So the tetrahedron can actually tell it. It can be 24 cells, 600 cells, 16 cells. They're all just made of tetrahedron, tiling the curved three-dimensional space. Depending on what the curvature is, yeah, right? It can be 5 cell, 16 cell, 8 cell, 24 cell. I don't know about 8 cell. But
The curvature is the inverse of the radius
yes.
of the sphere against the...
Mm-hmm. Yeah, so basically this is, just think about this as a curved three-dimensional space, and this is a Euclidean three-dimensional space. So in Euclidean three-dimensional space, if you want to tile the space with tetrahedron, the tetrahedron needs to be distorted. In this case, in this quasi-crystal, we can see how the tetrahedron got distorted.
So,
Yes.
mathematically then, is there a term that once you apply the curvature or the distortion, that
Mhm.
goes to zero and then it's not frustrated anymore?
Well, that's kind of what Klee is really wants to emphasize, wants to focus on. That's the curvature, thing. There's a curvature, which is one over golden ratio, and then there is this through the rotation or twist. There is this twisting angle. So how do they relate to each other? If there is a formula or equation, we can just do that nicely. That's part of the project. Yeah. Okay. So then there's a solution for geometric frustration through rotation, which is we kind of start calling it a Poland quasi-crystal because we presented it at the quasi-crystal conference in Poland. So we call it the Poland quasi-crystal just because it's a simple. We can't find any name that is shorter than this, but maybe we can name it in a better way later.
Poland has nothing to do with it.
No.
We probably should change it someday.
Yeah. You started calling the Poland
It was so easy.
quasi-crystal. Okay, so I will talk about that. I mean, that's the main focus. I'll show this, and this would be the main focus. So then another solution for the geometric frustration is through twisting. And then that's, we propose the fig and the compound quasi-crystal. So I'm not going to talk about this today.
What does that P stand for? Compound Poland quasi?
compound quasicrystal. Okay, so these two. So I will be covering. Okay, so the first one. The solutions for geometrical frustrations through distortion, which is the E8 to 3D quasicrystal. So when we projected the E8 to 3D, it is pretty hard because you're kind of crushing down 5 dimensions. And so Julio tried to do that, and then he did it, but he could only do it so that it is, so this is size of 600 cell. He could do it so that it's like this big, maybe like a twice or something. So it does not go very far. So we cannot see very much. You know, there will be other 600 cells, you know, around it. So we couldn't see that part. So but pretty much all the tetrahedron he got, I can equally get it from the projection of the E8 to 40. So you first project the E8 to 40, and then project the 40 to 3D.
Can you just clarify so nobody misunderstands? You mean 600 cell projections?
No, not just
So
600
it
cells.
wouldn't be 600 cells in 3D, it'd be projections of them.
Yes, the projections of the 600 cells. I mean, these balls, you can see them. So anyway, so that's why, you know, I have this E8 to 40 projection. What he did is it's a pretty big quasicrystal. So I just select the layer of that 4-dimensional quasicrystal and project it to 3D. And it gave me like a really big 3-dimensional quasicrystal. But because there's a difference between from E8 to 3D and E8 to 40 and then to 3D. Because of the Voronoi cell, when he projected from E8 to 3D, he used the Voronoi cell that, you know, like the kind of cutting, the boundary that he used, the cut window is slightly different than the E8 to 40. So basically, I missed some information. Like I did the comparison. There's some like some tetrahedron that is missing in this projection. You can see because when I show you, you will see some gaps. In those gaps, in Julio's E8 to 3D projection, you can see severely distorted tetrahedron there. So which I don't have it here. Okay, so I'm going to show you. Okay, so there are 2 types of projections when you project the E8 to the E8 to 40 quasicrystal, which is also Sloan quasicrystal. When you project the quasicrystal to 3D, there are 2 nice ways of projecting it. Because you know that the 4-dimensional quasicrystal has the 335 kind of symmetry, right? It's a 600 cell symmetry. So we could choose to project it. We could choose like the symmetry that is, you know, to project it into icosahedron symmetry, or we can choose to project it into a tetrahedron symmetry. So basically, this is a vertex first icosahedral quasicrystal. This is cell first the tetrahedral quasicrystal. It's kind of like oh, that's 600 cell. Good. So this is a vertex. This is a vertex first the projection of the 600 cell, which is the core of the 4-dimensional quasicrystal. So you can see at the core it's a vertex, right? So imagine you're in front of a big 600 cell, and if you line up with the vertex of the 600 cell and just project it down. Okay, so this is what we got. So basically the vertex is at the center. So, but the 600 cell also is made of tetrahedral facets. So if you line up with the center of the 600 cell, the center of the tetrahedron facet, one of the facet, anyone, does not matter. So if you line up with the center of the tetrahedron and then you project it, so at your in your projection, the center will be a tetrahedron, won't be a vertex. Okay, so that the second projection is the cell first, the first is the vertex first, and they have different symmetry. So I'm going to show you these 2. So here's an icosahedron, and you can see that the very center is a vertex. And around that vertex, 20 tetrahedron. I don't know if I can make it become normal. Okay, so then the second layer would be the tetrahedron, you know, face to the original 20 tetrahedron. But these are already distorted. Even the first layer is distorted. So we know the icosahedron is made of 20 distorted tetrahedrons, slightly distorted. The distance from the center to the vertex is slightly shorter than the edges of the icosahedron. So here too, these edges would be shorter than these edges. So there's another 20 in the second layer. And then, okay, so if I go back, and so you can see, you can feel a tetrahedron here and here at the original in the icosahedron node. Those are where the edges at. So there is another 30 of them on the edges. And then each of the, you can see this, there's a pentagonal cone there. And then at this position, you can add 5 of them. So it's another layer. And then, so there is a little bit asymmetry here due to, from 4D to 3D projection. So I think it's not perfectly icosahedronally symmetric. We were thinking either this is because of, when Julio projected from E8 to 40, there is always a problem from E8 when we project from higher dimension to lower dimension, crossing many dimensions. Like when when the points are very close to the cut window, to the boundary, whether the point should be included or not included. So there's some errors, so there'll be some missing point or some extra point. It could be because of that. But anyway, there is just a little bit asymmetry there here.
So I have a question. So is it still outstanding and not clear whether you can generate the identical quasi-crystal from between these two, E8 to 3D, and then E8 to 4D, and then from there to 3D?
I think we can, as long as we keep the same cut window. Okay. The original window that selected, if they're identical, I think they should be. Which means
your guess is that that's more like a computer
yeah.
calculating artifact.
Yeah, because I think he tried to resolve it. It was like, there were more points that are like that at the beginning. So then after he optimized it, and then most of the odd points are gone. So anyway. Imagine like from E8, right, when you project to 40, the Gaussian polytope project to 600 cells. But when you make a cut window, some Gaussian polytope get like fully was totally inside of the projection window, but some of the Gaussian polytope were only partially inside of the cut window. So that's why they look like partial 600 cells in 4D.
What decides the width of the cut window?
I don't know. It's related. You mean from E8 to 40?
Yeah, the cut window you were just talking about.
From E8 to 40, Julio used the Voronoi cell of the the E8 lattice. I just want to show you all these other 600 cells that is farther away from. You can see, right, besides the center one, you start seeing all these other farther away 600 cells. And they're made of like only 8 types of tetrahedron in this case. So that's a vertex first. And I want to show you the cell first.
Are one of the types of the 8 flat into an equilateral triangle?
Uh-huh. Yeah. So this is the cell first. It starts with a tetrahedron at the center. You can also see there is like little balls here, but the center of the ball is a cell, it's a tetrahedron cell. Let me just show you the very center. It's a tetrahedron, so you know that I'm not lying. And so the second layer, of course, is 4 tetrahedron. and then another 6 of them on the edges.
Is this the same thing as well? They're getting smaller as you're going up.
Yes, they got more distorted. Yeah, so but you can also see, yeah, this is like a little bit like a tetrahedron symmetry, cuboctahedron kind of shape. This is 57 group, by the way.
So is the distortion the frustration here?
Yeah.
Okay. So it's not the solution, like, yet.
Well,
Yeah, it's a solution.
yeah, it's a
Yeah, but not yet. This distortion is frustration.
Well, any kind of way of resolving it is, you know, it's just like when it is frustrated, it does not know what to do, so you do it with distortion.
Like in a way,
you do it with curvature, or you do it
in
with
a way, it
rotation.
doesn't exist when it's expressed. So it's expressed
Well,
as frustration. So it's in some sense it's been converted to. I mean, it exists as distortion. So the
Yeah.
frustration is an abstract idea that how are you going to express it in the form of distortion or rotation?
Yeah.
So how, is there like a way to quantify that then?
Yeah,
wonder
that,
if
that's
Saha
that's
and
that's
Missouri
yeah
wrote
that's
that.
that's the direction that we're going.
So
So-
Saha and Missouri didn't do any.
What they did it is through kind of different ways. They, you know, like there is, and they do also with distortion, and also there is some kind of a helical thing. They offered a kind of little different ways, you know, like they also do this, like kind of a little bit like what Glosser's group got, you know, a little bit kind of helical, kind of like a icosahedron, right? You attack icosahedron, another icosahedron on top of this one, so there is a kind of like a cylindrical things.
But they might not have
And after,
quantified it.
yeah, after the cylindrical thing though, because there will be, you know, it's a cylindrical, right? I think he also tried to curve them, and then when he curved them, and then there will be some gaps, and then so he's trying to fill the gaps in certain way. I don't know if he or other people did that, but that's what I remember. So anyway, so you keep going on, and then you got these other shapes. So just to give you some visual idea of this.
But when you keep going on and the size is increasing, you have more and more different tetrahedron shapes.
Not always, because it will stop at a certain point in time, because then you meet another 600 cell and everything starts from there. That's what I'm trying to tell you.
Right, it starts over.
So let me show you maybe.
And he is not deformed by the fact that he is farther from the
No.
center of projection?
No, not really. I mean, I can show you pretty quickly. You're going to see another tetrahedron that is, you can see another regular tetrahedron, really, you know.
How many shapes of tetrahedra did we?
In this one,
did
it's
we label?
8. In this one, it's 8, but in Julio's yield to 3D projection, it's 24 or something like that. So anyway, it's taking me too much time to show you that, but the center of these balls, they also have like regular tetrahedrons, some of them. If they're not perfectly regular, they're pretty regular, because you kind of see another 600 cell there.
But technically, we should say there's 7 tetrahedra here, because the flat one, the one that goes to complete equilateral triangle, that becomes part of one of the 7 shapes. Like that face becomes one of those 7.
Yeah. Okay, so these balls, the center of these balls should be tetrahedron too.
Each ball is a 600 cell?
Project,
Yeah. So just think about it, right? If you in the 4-dimensional quasi-crystal, if you make a slice, you slice one tetrahedron at the center. You just make a 3-dimensional slice, and then with a tetrahedron at the center, which basically facet of a 600 cell. And in this kind of slice, you're gonna see regular tetrahedrons everywhere. So this is a projection which included this regular tetrahedron and with certain thickness.
And
So it should include all these other regular tetrahedron as well. Yeah. Okay. So we're clear on this, right? And let's continue. All right, so I give you guys the name of the mathematical notebook so you can check it later. And so then, and this is the main part. So the solution for the geometric frustration through rotation, which is the polar and quasi-crystal. So just, it's hard to visualize, but just visualize the 4-dimensional quasi-crystal, right, as intersecting 3 spheres. like balls. And these balls kind of look like this. I just kind of made like look like this to give you some kind of visual, idea of what kind of look like. And if we can, and we can make a kind of a layer, a slice of a corrugated layer kind of thing. Like if you follow the surface of this ball, and then when they intersect with another one, you just follow another surface. Just keep going. Like it's still kind of a two-dimensional surface here in this case, right? But it's not Euclidean. It has curvatures everywhere. So but just do that, and then try to project it down. When you project it down, you can see, for this one, it projected down like locally. The center is more regular, and then become irregular when it's closer to, this area, the boundaries. But for each little, local sphere, you always get like regular at the center, more irregular as it, get further away from the center. So kind of get a little bit kind of like local structures like this. So that's why when we try to project a layer of the four-dimensional quasi-crystal down, because it is made of this little local curved three-dimensional spaces, not infinitely big, kind of three-dimensional space. That's why we can deal with each local one, right, individually, and then we can resolve the problem. It does not have to go very far away. The tetrahedron gets super distorted, like continuously distorted, because it would stop, because there will be 7 types and then stop, and then here 7 times stop, or it does not even go to the 7 types, because sometimes the sphere is not the half sphere. Because if we took a half, if we cut the 600 cell in half, we have this half 3 sphere, then we have 8 tetrahedron types. But if some of the 600 cell is only cut by this much, like very small part, then you don't even need all 7 types to express that local area. Okay, so so this is kind of what I did. This is the best picture. But anyway, so these are the 600 cells that intersecting, in the 4-dimensional quasi-crystal. When they project to 3D, this is what they kind of look like. And then I was trying to, they kind of look like that, but I have to separate them into different shapes, because sometimes the 600 cell can be almost the whole 600 cell projection. Sometimes it's only a little part. So I think I give it I don't know why I don't have it here. There are a few different types. There is a Icosahedra, because when we slice the 600 cell from the equator, and then we got the Dodecahedron. Okay, so like this, for example, just imagine this is as the 600 cell, which is it's not, but imagine if we slice these things from this equator, we got a bigger shape, right? Here we got a bigger decagon. So in the 600 cell case, we got a Dodecahedron pretty big. But if we slice it from here, not at the equator, from here, we got a Icosahedron. And if we go more up, we got a Dodecahedron and then Icosahedron again. So that's kind of the order. So basically, I could be getting an Dodecahedron, which I needed more tetrahedron to fill in, because if this is a sphere I got, and this is a convex hull, which is a Dodecahedron, I need to fill this much of tetrahedron down, which is 300 of them. And if I got only a Icosahedron, like upper, I got less tetrahedron. And if it's a dodecahedron, I got even less. I got the smallest icosahedron, it's only 20 tetrahedron there. So depending on
how many vertices on the full projection to 3D?
How many vertices?
Right.
Well, it's a 1 plus
the vertices
30.
on the outside, just the convex hull, the shape, that is the projection of the 600 cell to 3D, that
The
shape,
whole shape? It's Icosahedra.
on the outside,
Uh-huh.
has that many vertices.
Yeah, the most outer layer.
So 32,
Yeah.
that's 32,
30.
30 I used.
Yeah. Okay, so so that's why, if I have a dodecahedron, I fill the dodecahedron with this. I think that's what my solution was. And if it's a dodecahedron, it is filled like this, So, and then I think you guys still remember the projection of the 600 cell. Certain layers, they just look like this, but these tetrahedron are distorted. But here, I left a little bit of gaps, if you can see, just like tiny gaps. So because I want all tetrahedron to be regular. So this is how I filled the dodecahedron convex holes, and this is when I filled the icosahedron convex holes. So there is also a little bit of tiny gap there, and this is the big dodecahedron convex hole.
So those yellow things in the upper left image, those are projections of 600 cells, aren't they?
Yeah.
And those are not icosahedra. So I'm asking how many vertices on that shape.
But that's not one layer, it's not vertex transitive. I don't think so.
But whatever that shape is, do you know how many vertices there are? Are there 60?
I don't know. I don't remember. Because there is a 5, there is a 6. So I think it's dodecahedron plus another maybe 20, plus another 20 or 12 of them. So yeah, it's dodecahedron plus icosahedron or dodecahedron.
So definitely not 60.
Should be another 20, I think. Yeah.
So that'd be 52.
Yeah, probably 50. All right, so when I do it this way, I think this is actually the bigger dodecahedron. In the paper, I think it has more. These are our dodecahedrons. I think this is already when I try to put them together, what they look like. But I think I have better images and notebooks later, so be more clear. So then let's talk about the other method, which is kind of like match up with what I did. And then I'll go back to make that part more clear. I'm sorry, so just bear with me a little bit. So this is what Julio researched, and then we were both kind of looking for solutions for this, for regularizing the tetrahedron because they're distorted. How do we regularize them? And then so he bumped into a paper that talks about the decorated amount tiling. The amount tiling is kind of a three-dimensional penrose tiling. It's made with prolate and oblate rhombohedron. So that paper talks about how to decorate these two shapes with tetrahedron. And then after you decorate it, then the whole quasi-crystal would be made of tetrahedron instead of those two shapes. But that decoration is more complicated. Each shape, it has a lot more tetrahedron. So Julio simplified it. So he decorated the prolate one with this. Oblate, this is a prolate rhombohedron. He decorated with these tetrahedron here. So the difficult about this is because the rhombohedron has to put together face to face. So the face has to match. How you decorated this face, for example, has to match with how you decorated this face because they match with each other. It's the matching rule. So he played it with that, and then he successfully, decorated these two shapes, all matching, all fine, and then but there is some kind of I think I believe even in the end there is still a choice kind of thing, a binary choice. A tetrahedron can be more favoring this cell or that cell. So you have a choice. But if you say, okay, I always want to favor this one, that's fine. But it's kind of like a personal choice thing.
So do you have to remove some tetrahedron when
Yes.
you glue the things together?
No. When they perfectly match, you don't have to remove anything. Yeah, but if on the symmetry part, the tetrahedron can be favoring either this one or the other one. And so this is the, I think, the RT, the rhombic tetrahedron. After, he figured out these two types of cells, and he built out the rhombic tetrahedron with tetrahedron. It looks really nice. And this is a bigger quasi-crystal on that. And this quasi-crystal surprisingly matched with the quasi-crystal that I built. There is a little bit difference, I have to say. There is a little bit difference because when I fill the Icosahedra, there need to be 300 tetrahedron in it, and then that's really hard to do because there'll be gaps. So what I did is I have to remove the outer layers and to match with the Julio's. So because when I remove the outer layers and all the inner layers are pretty nicely packed, you know what I mean? Because when the Icosahedra, right, and these it's on the equator, and the tetrahedron at the boundary are severely distorted. They almost occupy no space in, when you talk about the Euclidean, this convex. So I have to remove those. Otherwise, I have to make this Icosahedra bigger to fill in these tetrahedron. And that will make, that does not work, because if I just enlarge the Icosahedra, then what about the other cells? I have to enlarge them as well. Then I would just end up with big gaps. So what I did is I removed these layers and then match with the quasi-crystal. I do have a mathematical notebook of the two quasi-crystal matching with each other really well. Okay, so this is a better way of looking at that. So forget about the original slices. This is a better way of explaining my idea. So in the E8-240 quasi-crystal, so if I make a slice, make a three-dimensional slice, and then these are the convex holes that I got, make a three-dimensional slice from the center 600 cell, I got the Icosahedra, and then near the Icosahedra, I got the Dodecahedron cells around it. So basically, for the center 600 cell, I selected its equator. For near the 600 cell in the four-dimensional quasi-crystal, the other 600 cell is kind of like a little bit below it. So I only slice it through like this part instead of the equator part. So I got a smaller convex hull. And so then, because I got a smaller convex hull, and then I have less tetrahedron to fill in that one. Do you guys understand that? Yeah. So then, and then I have the dodecahedron, Icosahedra, pretty much only these two shapes, but then I have this gaps between them that looks like Icosahedra, but it's a truncated Icosahedra. So the truncated Icosahedron, I don't need it to fill all 20 tetrahedron. I only need to fill part of them. I think instead of all 20, like some symmetrically, I can remove certain tetrahedron there to fill the gap. And so this is my proposal for the dodecahedron. This is so this is dodecahedron, Icosahedron. And then the Icosahedra, I think I mentioned earlier, I didn't mention here. So yeah, the Icosahedra was filled in this way. And then that's one method. I also use another method. So each of these balls, no matter it's big or small, I kind of filled it with this kind of spiky ball I call the shape. So each of these balls just fill in this one. And then I call these kind of gears. So if you put these two together, and then they perfectly match with each other. This pokes out, and the other side, the tetrahedron from this side would match with it in a nice way, like rotated this much. And also, I think on these bigger balls, between the bigger balls, I believe I used this ring to lock them together, because there will be gaps, and then lock them. It's been some time, so I remember I used 2 or 3 methods, just like how Julio played with the face decoration. How I decorated this, I also kind of played a little bit. And this is kind of, I think it's more symmetrical. When I do the twisted version, it's easier for me to twist the tetrahedron than this type. So I got my quasi crystal that looks just like a Julio's, and then if we each like kind of tweak a little bit, we can make them kind of identical.
So what you didn't cover is, or you didn't go into, is I don't understand much about Julio's quasi crystal. Like I don't.
It's the amount tiling.
No. Well, I don't understand much about how he decorated the Amman tiles, because I don't know if there's an infinite number of ways you can decorate it. I don't know, meaning that you said that they have to match, so that's one requirement. Are there an infinite number of ways that they can be arranged to match?
This is for maximum packing density. Yeah, it's if you want maximum packing density, and then the smallest number of tetrahedron to decorate each cell.
So he feels he proved that? Because the other paper, he modified what the other paper did.
Yeah,
so he did
the other paper is less dense because they decorated each cell with more tetrahedron and with a bigger gap. So I can only say you cannot do less than this. If you do less than this, then you're gonna end up with really ugly gaps and
But
not.
Did he do some sort of proof, or is
Not
there
any kind of rigor proof.
So
But like I can see, like this is all. This is to me like I can only say it. It seems to me the densest way, the nicest way to decorate it. It's not like many ways. This is just one of them. I think this is the best to me.
But you didn't search because he did that project, so you didn't.
Oh,
search
I
for
participated
for the decorating the Amman tiling.
Yeah, we always talk. I mean, it's always his work, but I always talk with him, so I know everything he did. He also presented, and also we write a paper together. So.
Which one is more dense between this and the Amman? The dimmer and the Amman?
Well, I said if I do it the way to match his, instead of leaving all the tetrahedron there, if I remove the outer layers to match with Julio's, then they should be having identical packing density.
Did we show that or state that in the paper?
Yeah.
That they have the same packing density?
Well, they are same structure, basically. So, and then, but the things, because at that time I was more focusing on the twisting, so for my version I was mostly just showing the twisted. And the reason that I went to this one is also because it's so easy for me to twist them in a symmetric way. So anyway, so this is a twisted version. That's why I went to this, because if I use this, then I can just twist this cluster in this way, very symmetrical, because 20 group, we always know how to twist it. And then for this one, and then so I can show you maybe a model that when we twisted them, these are just like perfectly touching. And so kind of, but I did have to, I think, move them out a little bit to have some gap there. So if I put them all together, that's the overall shape.
I see that this is A is a non-twisted 20 group. It's an A shape.
Oh, okay.
When you twist it, you have the 20 group.
Yeah.
Oh, right.
One-to-one correspondence.
Because the center of A is a shared vertex.
Yeah, the inner is a 20. So anyway, this is what we did, but I wanted to explain why we did it that way. So we each intuitively kind of went there and got that structure, but it's after that we try to justify it, like why did we even do that? So the next I'm gonna talk about that. Right. So how do we go from this curved, this three-dimensional space to Euclidean space, and to make the tetrahedron stay regular? Like, what's the best way? Like, I feel like from the curved 3D to Euclidean space, this is much easier than we project them, distort them, and try to regularize them. So just make all the tetrahedrons stay regular and then move them to Euclidean space. So that's kind of like my motivation. So the way to do it is, like, if we have a sphere, have to always borrow this big sphere. How about a sphere like this? Okay, so imagine there are regular shape here. So if we wanted to project it to this space, let's move this space up here. Okay, let's move it all to this level. So the first one stay regular, fine, right? It's easy. But the second one, you see, it has an angle with this space that is gonna be moved in. What should we do? To make it stay regular, if we projected it, they would distort. So the only way to make it regular is to rotate it. Okay, to rotate this facet up, to rotate it, either stay here or just rotate it up. But you rotate it so that this space is parallel to the space that is gonna be moving in, right? So you rotate this triangle, and then make it parallel to the two-dimensional space, in this case, that is going to be moved in, and then you moved it there. So it's always regular, right? So I think Julio and I did it kind of differently. He keep this. Somehow we came up with this exactly same solution again. We didn't really, talk a lot before that. So what he did is he rotated, for example, this triangle. He just rotated it and keep the center here, and then moved it up. But because there is a smaller space here, right, for the tetrahedron, I mean in the 40 to 3 decades, and he just shrink it a little bit. So stay regular, but he shrink the tetrahedron a little bit. But what I did is, I just kind of, I keep this tetrahedron here. I mean, in this case, it's a triangle, like in 40 to 3 decades, it's a tetrahedron. So keep this tetrahedron here. And the second tetrahedron, I rotated, I keep this edge here. I rotate this part up so that it goes to this space. So that's what I did. And when I do that, I bring everything up together, like all the rest, I kind of that is connected, I bring them all up. Like while this point going up, everything comes with it. You know what I mean?
Will it not be the same effect if you squeeze the center? You'll have the same effect. Instead of pulling everything up, if the one which is on the top, if you push that down, you'll get the same effect.
Yeah, it's the same. It's the same. I'm just because this is easier for me to explain. So just think this, the space is here. And so, but because eventually they're all gonna be in the same space. I'm just saying imagine these tetrahedron, I just put this up to this space. And then because this is going up, everything that connect to the point goes up also. And then, and so then these facets also has one point there. So now I rotate the whole thing also. Keep this point the same, I rotate the same thing up. You know what I mean?
When you did that, Julio compressed his. Did you expand?
I didn't. Yeah, that's the thing. I was trying to expanding everything,
but
and he was.
It would be equal, but then it would be spread further out.
Yeah. So, the thing is that he would have a smaller tetrahedron on the outside, and I have all equal tetrahedron. So then, but the thing is, in my structure, I have the gaps. So then, but the thing is, eventually, his solution will not get the Pauli quasi-crystal solution because all those tetrahedron are equal size. So he just proposing, that's kind of a nice way because you can use the size of the tetrahedron to measure the curvature. But the thing is, our purpose is still to try to keep the tetrahedron not only regular but the same shape. So I mean that's just his proposal. But I did it more. I don't think he actually did a lot. Maybe he did one model on that. But anyway, so I'm going to illustrate this one. I'm going to show you this notebook. So I will just show you some picture first. So for example, this is these triangles are in a two sphere, which is an icosahedron, right? So it's in a curved two-dimensional space here. It's a curved two-dimensional space here. So what I did is I keep that point at the same position. I rotate everything up, and then it will become this, and then there will be gaps. So like that, and then that's what I did for. This is how I got from this structure, I think, to this structure, and you can see this structure. You can see those little gaps. This is how I just rotated everything. I'm gonna show you a notebook on this for the procedure.
Does the CQC embed in the Poland twist?
I didn't check that. I don't know, actually. So let me.
Because if it does, then that's the solution I've been looking for. The Poland twist is the completed missing part of the CQC. If the CQC embeds.
Yeah. I guess in a way it should. I don't know. I mean, I think it's worth checking on. So this is a. So I first in this notebook I explained how to do this regulations procedure. So get the data of the 4D quasi-crystals that select the part of interest, start from a small patch. This is approximately 600 cell, which is the curved version of the 3D quasi-crystal. Get the central list of all tetrahedron, and then plot the 3D projection of this quasi-crystal, which is a distorted version. Get the central list of a tetrahedron on this quasi-crystal, so that's all the centers of the tetrahedron. Instead of projection, rotating each tetrahedron from 4D or curved 3D to the flat 3D plane using the angle made by the center list in these. Okay. So now that's it. Reminded me how I did it. Actually, I rotated the whole thing, because their center. This is the plane that they're gonna project it to. This is their center. I actually rotated the whole thing up, like put their center at the plane, and then I rotated that part around its center. So this is what I did. Right. So I just imagine this facet is here, and this is the plane it's going to. So I get the center. I rotated the center up. So in this way, I don't have to make it shrink in the small space. No. So I rotated it up, and then I regularized. I mean, I rotated the whole thing up, and because the tetrahedron is at an angle with the plane, so I still need to rotate the tetrahedron to be parallel to the plane. This is what.
When you say the whole thing, it is
one cell.
One cell.
Yeah, for each cell, that's what I did. So and then I feel, like instead of projection, okay, so regular unstable equilibrium. So what we get should be a regularized 3D quasi-crystal, a unstable equilibrium state. When I say unstable, because there are gaps. When there's a gap, there is a freedom for it to move this way or that way, to shift a little bit. It's not so stable. To bring this unstable state into stable state, this is what I try to introduce the twist. Right? So if I make the 20 tetrahedron even in spaces with the gap there, so then the tetrahedron can wiggle around. So instead of that, if I twisted it, they lock into this position, it's more stable to me. Anyway, that's just a physics concept. So, okay, start with this. And then, so this is just what I did. It's not, this is for projection and then become distorted. And this one is through rotation, like that. And then, this is just I was trying to find the 600 cell centers in the quasi-crystal. I think I should show you the smaller regularized. If we want only to show the first, okay, I'll just show this one because there are more tetrahedron here. Why is it like that? Why is it like that?
Control. Control on the mouse wheel.
Zoom out.
Yeah. You have to be delicate. No. Not control, then click and drag.
I think it is drag.
Yeah.
Okay, so let me put 20 there. All right, so this is 20 tetrahedron. So this is is that our Icosahedron? It looks so weird. It is.
It is.
But
No, it's like 2 5 groups, isn't it?
Yeah.
Like stuck together.
Yeah, that's what it looks like.
Wait.
It looks weird.
No, I don't think it could be, because every time she goes to a vertex, it has, oh no. See, there's the vertex.
oh, because that's because I added another. Yeah,
That's
so
weird.
I think it's maybe because the view, the
Right.
perspective is weird.
But it's 20, because every vertex is 5.
Yeah, this is the Icosahedron. But anyway, so when I try to rotate it, rotate it, you can see there is gaps there. So this is when I rotate the tetrahedron from a curved 3-dimensional space to the Euclidean 3-dimensional space. This is the purple one that would look like. And then if I go to more tetrahedron, yeah, it's just a weird perspective. So if I don't show the rotated, this is what it look like. If I show the rotate, this is what it look like. I can maybe make a 200.
Ike has 40 tetrahedron.
Yes. Too much. That's too much. 200. Actually, 100. Okay, you can see this shape.
Kind of hard to see, but.
Yeah, there's a purple and red. So
Zoom back in again a little bit.
you can see the red, right? The purple is kind of like has a bigger structure because, you know, it's all regular. So Phil need a bigger space, bigger convex hole for it. So, but anyway, so this is what I kind of achieved for this. And then I think after this, you know, we'll try to twist, but I don't think I didn't do it. It's very, so, I mean, this is kind of like, if I make it a less tetrahedron, this is to try to justify what we did for the pollen quasi-crystal, because you remember this structure for the pollen quasi-crystal, right? It's the dodecahedron that I filled this structure in. Okay. And then this is, I have a notebook that is matching these two methods together that you can go ahead and check them if you want. So I don't want to spend much time on this. Oh, just for Julio's method. So the paper, this is how the paper decorated the rhombohedron. You can see he used lots of tetrahedron, but then he leave big gaps there. So Julio kind of modified it to decorate in this way. So less tetrahedron. I mean, they decorated it using irregular tetrahedron, not regular, irregular. So slightly irregular tetrahedron. So Julio, first of all, he tried to shorten his edge length, you know, remove this tetrahedron there and to make it shorter. And so the tetrahedron can stay more regular, because this is like when you make a more tetrahedron to decorate each cell, and the tetrahedron can become more irregular. All right, let's continue. So I have covered what the pollen quasi-crystal is, and also kind of give you some idea that why that kind of regularization scheme can be justified, you know, or can be more systematic than just arbitrary, you know. So these are steps that I already talked in the mathematical notebook. Okay, this is what Julio did, I think. Yeah, this is his result. but I think he starts shrinking tetrahedron here. That's it. So and then the other way, the fourth way that I mentioned is through the twist, which kind of would be related to fig and a compound quasi-crystal. That part itself, like compound quasi-crystal and fig themselves, are like a big topic. So we can talk about that later. Yeah. Thank you. So, Klee, do you still want to make quizzes in this? This and then the previous one.
I think so.
Okay, so should we do it on Friday?
Yeah, I worry it'll be hard in this one because there's not a lot of math in this one that you can give them. You can give them general things. So Fang, can you sit down?